transformers? So what did we learn last week? Transformer. Did I teach transformers? Okay. And then did I only teach transformers? Okay, I'm pretty sure I did mention about it. I must have spent 2 hours talking about something beyond just transformer. So tension mechanism? We did learn about the tension mechanism. Okay, that's good. That's good. And then what did we learn near the end of the last week?
And then we used to frame the transformers language model.
Okay. Yeah. That's closer.
Mask model.
Right. I did mention mask language model, right? Hopefully, I'm not hallucinating what I told last week.
Large pre-train model.
Sorry.
Large pre-train model.
Did I mention that one? Okay, so I might be actually hallucinating, not talking at all. But we did talk about the mask language model. So we're going to continue from there for just a bit before we continue to the next topic, that is the semi-supervised learning. So the point of mask language model to somehow generalize the notion of next word prediction in a way that we're going to try to predict whatever is missing, regardless of where they are, given whatever we have observed. And then there, what we talked about is the objective function. So for training, so this time we're going to maximize it. We're going to go through all those n many examples, and then we look at the expectation over the missing and observed partitions. So if you remember, Tn corresponds to the length of the nth example, and then given that length, we can partition all these Tn many words into the observed and missing. Now, how are we going to partition it? That's actually up to you to decide. And then that's the reason why we're going to just use this abstract notion of T there. So that's some implicit distribution that you're going to define by defining how to sample these partitions. Or we're going to consider all possible samples of the partitions according to the distribution you have defined. Then what we look at is what is the probability of I going from 1 to Tn missing. So Tn n corresponds to the number of the missing words within the n example sequence. Then we look at the probability assigned by our model to the correct missing word, given all the other observed variables. So the objective function refers to what is the log probability assigned to the missing words given all the observed words. And we're going to look at the expected value of the log probability over all possible ways in which you can partition the words into missing and observed. And we again look at the expectation or the average over all the examples in the database. And the reason why we look at the expectation at the very end is to turn it into a stochastic gradient descent. So in practice, we can't really compute this exactly, not because of the summation outside, but because of the expectation inside. Because what is that distribution? If you don't know the distribution, but only to sample from it, computing the expectation exactly is very difficult. If you don't know how to compute the expectation very well, then you can't really compute the gradient of the expected value either. So what we do is we're going to use just like how we view this average over the training instances as if computing the expected, for example, loss function, where the distribution was defined to be uniform over all the observed training instances. We're going to do exactly the same thing. So we're going to use a Monte Carlo approximation where we draw number of samples, could very well be just one, from this partitioning distribution. So we're going to pick one example. We're going to randomly partition the input and the words into the observed and missing. And then given that one, we're going to compute the log probability of the missing words given the observed words. Then we use that to compute the stochastic gradient. And what we do from there on, we just do it over and over and over again, right? So that was mask language model. And then one thing that was confusing was why we call this a language model, because a language model, yes?
What is the subscript of the last X?
Last X is XOTO. Yep, so TO was going to the number of the observed words in the input or in the sequence. And then O of I tells us the I observed word. Okay, so the index of that one. So the question is, okay, why is it language model? Because we defined the language model at the very beginning, not very beginning, but at the very beginning of the language model lectures to be a black box that is going to tell us how probable a given text snippet is. How probable this the text or the sequence is. But looking at this, it's not really clear how we're going to actually turn these conditional probabilities that we're computing, right? So we have, in fact, t many random variables. We're going to now say that here's one missing variable, and then here are a bunch of observed variables. Now, we now know how to compute the conditional probability distribution over this missing variable given few of the observed variables. So how do we actually use the information to get us how probable, or how to make this tell us how probable a given sentence is? It turned out there are many different ways to do so. And in fact, every one of those ways defines a different distribution. So this is a really interesting kind of thing that we can talk about from the machine learning or the statistics perspective, is that when we think about a distribution, probability distribution, we often think about either having access to so-called probability mass function or the probability dense function, or sometimes you're interested in the cumulative, let's say, density function. And then in our mind, we often have this notion of we need to be able to compute the probability assigned to a sum event, or the event set, or the event space. But then is that really true? Is that the only way to define a distribution? It turned out that that's actually not the case. There are many different ways to define a distribution. One way is to simply define how we generate samples. So without even knowing what the distribution is, by coming up with some kind of stochastic process that's going to get us a bunch of, let's say, samples, even if we don't know what is the probability assigned to each and every sample we generate from the generating process, this generating process, stochastic process, in fact, defines implicitly some kind of distribution. Now, another way to think about it is that what we learned at the very, very beginning of this course is that if we could assign some score to any of the examples, then even if it's extremely difficult to turn that into the probability itself, we know that there is some distribution defined there based on the choice of the normalization scheme. Of course, we can now decide to choose a very different normalization than the softmax that we've been following, and then we'd end up with a different distribution. However, still our choices for the normalization scheme and the score function gives us a distribution that is implicitly defined. It's not explicitly defined with some analytical. So we're going to look at 3 different ways to do so here with the mask language model, and it turned out all 3 of them do result in 3 different distributions, although it's quite difficult to show that there is a case. So the first way is to turn this mask language model into autoregressive language model that we have learned very, very carefully over the past few weeks. And then here we're going to assume that we will do the left to right ordering. Because if you recall from the autoregressive language model, we could choose any arbitrary ordering of the variables as long as we can fix it in advance. Now here, let's assume that this will be left to right. And then it turned out, assuming that this distribution over the partitioning does cover all possible ways in which things happen, then you notice that this mask language model can compute all the conditional distributions of the probabilities that we need in order to build the autoregressive model. How we do that? Let's say I want to compute the probability of a sequence X. I'm going to go over each and every word. Then I'm going to look at the probability of the key word, the correct word given all the previous ones up until xt minus 1, while I'm going to set all the future ones to the mask token, the special token that we introduced. So what does this mean? It just means that we trust that this mask language model has learned to observe everything that comes before, and then was missing everything that comes after, and it tries to predict the center one. And then if our partitioning process T there, that this create T was indeed defining an implicit distribution that assigns some non-zero probability to this particular combination of the observed and missing words, then this must be a reasonable, let's say, conditional distribution that we can use in order to now induce an autoregressive model. Now, there turned out to be a couple of the issues, although this is actually precisely how we prove that the masked language model is indeed recovering a language model distribution given the data set. But the issue is that first of all, the space of partitioning is pretty large. Space of partitioning is pretty large. For every word, you can imagine that you're tossing a coin, and then if it lands head, you're going to say observed, tail, missing. And then what that means is that there are exponentially many possible ways in which things can, partition. The sequence can be partitioned. And what that means is that this is a one particular way in which the sequence can be partitioned into the observed and missing words, given this exponential size. So we often, or the model, the masked language model often does not see this kind of, let's say, split, enough during training to be a good language model. Although, as you can imagine that in the limit of the infinite time and infinite, let's say, capacity, this indeed, the masked language model does converge to the autoregressive model, right? Because why is that so? Autoregressive model, what was the way for us to build an autoregressive model? The most naive way? To build a table. Now, what was the table? All the previous words, and then the current word, and then look at the count. Masked language model is simply extending this table dramatically by all the observed words and then missing words. And then we know that if we ensure that implicit distribution by that partition process does cover all possibilities, this table is going to cover every entry that's going to show up in this autoregressive language model table. That's why it works in theory, but in reality, it turned out to a pretty lousy way to turn the masked language model into a autoregressive language model to get the score or tell how probable a given sentence is. Was there a question?
Yeah, just kind of to clarify what you're saying. So like in a situation where maybe that last X capital T is not masked, that's a situation where we're not approximating the autoregressive model.
Right. So if we, let's say, observe any one of these,
right,
then this equality doesn't hold anymore. Right?
I see what you're saying.
Mm-hmm. So in a sense, masked language modeling is a superset of the language model, autoregressive language model. So in this sense, masked language model is indeed a language model because we can if we look at the autoregressive language model as a language model, because we can always turn the masked language model into autoregressive model, it is a language model. But in reality, this one doesn't really work well, sadly. Now, what would be a second way to do so is to turn this masked language model into a score function. And as we just talked about it, if we can give some score to each and every possible event in the entire event set, we can turn that into a distribution. So what we're going to do is we're going to use the idea of pseudo likelihood. The pseudo likelihood, which is a really old, let's say, concept from I think the 71 or something like that by the book, is that often it's difficult to compute the full probability of an actual observation, especially when it's very high dimensional, and then estimating that is difficult because we run into this issue of the curse of dimensionality, right? Because as we add more and more dimensions, the space grows exponentially. So instead, is there a way for us to reduce that into the linear complexity or the linear space? And then the pseudo likelihood is a one kind of, let's say, approximate, but quite interesting way to do so. Pseudo likelihood or the pseudo log likelihood is defined as we're going to go for each and every variable, but one thing you notice is that it's not a product, but the summation now. And then we will look at the sum of the low conditional probability of the word at that position given all the others. And this is pseudo log likelihood of X. And then it turned out that there are some cases or the very strong conditions under which the pseudo-loop likelihood does, the estimating the conditional distributions does converge to as if we are estimating the full conditional loop probability, although those conditions are very out of the context of this course. But we're going to use this idea of the pseudo-loop likelihood, and then what we're going to do is we're going to use this to score a sequence. And as you can see, that in this case, we give as many observed variables as possible to recover just one missing variable. This turned out to be way easier than trying to leave out most of the information and then trying to predict one, let's say, missing variable given a very small number of the observed variables. Now, once we have this score, what can we do? As we have learned, we can turn this the probability this score into a probability by using so-called soft-text function. So it's going to be exponentiation of this score f of x, and then we need a normalization. Where is L, so the normalization is done over all set of all possible sequences, all possible text sequences. So we know that the mask language models are definitely predicting this conditional distributions pretty well. So we are going to turn this mask language model or the mask language model's conditional probabilities into the pseudo loop likelihood of the sequence, and then say that if this is the score that we're going to assign. Pseudo loop likelihood is not low probability because once you exponentiate it, they don't sum to 1. Unlike the actual loop probability, which you exponentiate it, they sum to 1. So we need to explicitly normalize it so that it's going to sum to 1. And then this normalization, unfortunately, needs to be done over all possible text or all possible sequences that can be formed using a vocabulary that we use. Then that turned out to be very difficult, as you can imagine. Yep, question?
Yeah, I was gonna ask, is it all possible sequences of the same length as the observed sequence, or just all possible sequences?
It's up to you to decide. So this set of all possible sequences is actually the set that you need to define. And then it can very well be an infinite size set. That's fine as well, as long as there are some conditions that you need to put, but it can very well be an infinitely large set. So yeah,
What is that for?
the snippets.
Snippets
Yep, text snippet.
of the length L.
No, I mean, no, there's no limit. There's no limit. So as you can see, one difficult part is that it's kind of difficult, if not impossible, to compute this normalization constant. So that makes it a bit tricky in 2 aspects. One is that if we cannot compute this normalization constant, we cannot in fact train this mask language model as the language model to start with. But that one is fine because it turned out that we could just train a mask language model to get all those conditional probabilities correct, and then we're going to turn that into this distribution. The second difficulty is that if we don't know how to compute the normalization constant, that actually almost directly implies that it's very difficult for us to sample from this. And then here, it turned out that we really don't know how to sample from this distribution directly. So then we could use some kind of importance sampling by defining some nice proposal distribution, sample from it, and then reweight them. All those things are possible. However, in general, sampling from this distribution turned out to be very difficult. But the really nice thing is that it turned out that this is a really nice distribution. So according to some of the recent papers, if you sample from this distribution directly using some kind of techniques from the that you're going to learn from the other courses, as for data science as well as computer science, you actually do get a very well-formed text out of it. What that means is that the distribution defined in this way, or the implicitly defined via this pseudo likelihood, is a good distribution. Now, the third way to go about is that let's forget about how we define or how we can write the actual probability. Do we really need to define the probability? Because as we have seen here, it turned out that we actually don't need to write a distribution. We just need to know how to sample from it. And then the process by which we sample, under some conditions that are pretty mild, are going to define some distribution for us. So let's say in this particular case, we can think of masked language model's conditional distribution as some stochastic generator. And all we do is we just train it. So let's see. We're going to start with some, let's say, random sequence, x tilde. So first, we're going to draw the length from some length distribution. And then this length distribution can be estimated from a training set as some kind of exponential distribution or the Poisson distribution or whatnot, whatever you want. So this is going to be some length distribution. And then you're going to randomly initialize a random string of length L. And from here, we are going to loop through. So for K, going from 1 to capital K, well, capital K can be whatever the number you want to decide to use. Larger the better, but there is no notion of a clear notion of the better or worse. So K can be anything. Then you're going to uniformly, sample an index I at random. And then we're going to replace that ith word in this x tilde sequence by sampling from this conditional distribution. And we're going to put mask there. And then we just do it for k times. And then whatever we get x tilde at the end of this loop is going to be one sample from this implicit distribution that is defined by this stochastic procedure. Now there comes a really interesting question here, is that why wouldn't we just then run it indefinitely? The weirdest thing is that if we have a finite k, then we know that there exists some distribution from which we got all these samples. But if we take the k to the infinite limit, the weird thing is that this may actually not define a distribution. That's a kind of, let's say, crazy thing, because this loop may actually start, let's say, can I say that cycle through the different distributions and may never actually converge to a single distribution. So, but with some, let's say, finite k, we just run it, and then we say there's one sample, we just run it indefinitely, and then all those sets of the samples that you're going to get are going to define you an implicit distribution over the language. Now, what is the issue with this approach is that you can't really get the score of any given sentence. You can sample very efficiently from this distribution, but you cannot get the score out. But these are the three different ways in which you can get the language model out of the masked language model. Question?
Yeah, sorry, is the mask there, is that the only thing that's masked?
Yeah.
Is XI?
Yeah, it's just X, Y, XI. So why? So that's actually a really interesting thing that you just pointed out, is that if you look at the second one as well as the third one, we are always just sampling or the scoring based on the conditional distribution where only one variable is missing and all the other variables are masked out. So why are we doing this? Why aren't we using a case where only some of them are observed? The reason is actually, it goes all the way back to the last week's lecture, which none of you remember, it turned out, at the very beginning of today's lecture, is that we made one assumption when we built a masked language model, is that the distribution over the missing variables, given the observed variables, is factorized. That is, that all those missing variables are mutually independent, conditioned on those observed variables. So the distribution we get for the multiple, let's say, missing values, given all the remaining observed variables that we get from the masked language model is of a very low quality, because it cannot really capture the conditional dependent structure among the missing variables. So that's the reason why when we use it for this purpose of defining a distribution, we almost always stick to the conditional distributions where only one of the variables was missing and all the others were observed. Very good question. All right, so that's why we call masked language models And this mask language model is often referred to as BERT these days. That's just because the Jacob Devlin decided to call it a BERT back then. And that's what everyone is calling it. And it's a very successful example of this mask language model. And mask language model in general can be is a special case of so-called denoising autoencoder, which we might actually go through today if time permits. And once training is done, we can actually use it for various purposes, such as sampling from this model. All right, so is there any questions before we move on to the actual this week's content? So
what I didn't understand the difference between the second and the third. Like both of them we're just masking one of them.
Yep, both of them are masking one of them at a time. So this one, we know what the distribution is. Analytical form, we know the analytical, we don't know how to compute it. Here, we actually don't know what the distribution is. We know how to sample from the distribution, but we don't know how the distribution looks like. That's the difference.
I mean, can we imagine there's like a mask bracket for the number 2 that you just did?
Oh yeah, sorry about that. Yeah, so the mask bracket is there between the xt minus 1 and xt plus 1. All right. Any other questions?
What is number 3 called? Like, if you want to learn more about that technique.
Yeah, so that good question. So there is no like a kind of let's say T name for this, but in machine learning context and recently, there are 2 different let's say areas under the so-called Bayesian or the probabilistic inference that does work in this kind of implicit distributions. And then one is called the approximate Bayesian computation, ABC for short. And then the other one, a bit more broader concept, is called simulation-based inference. So you can imagine that you have a simulator that is generating some, let's say, observations. Now, can we infer what the underlying distribution was, or what kind of, let's say, unknown variables were used? So I guess you can look into those simulation-based inference. Generally,
To compute the score of this third one, we could just do it like this 2, right? Compute the score.
no, but that's not going to be the same distribution. So the distribution here, as you can see, it doesn't have k there. On the other hand, here we have k, so it's very unlikely they're going to be the same distribution. Now, obviously, you can generate a bunch of samples, train an auto-regressive language model on those generated samples, then you'll be like, oh, that is the distribution. But then if that were the goal, then you just train an auto-regressive language model from the beginning, right? Instead of training a mass language. All right. Good. So there comes always a question of why we are learning all this, let's say, techniques to build and train a language model. We did talk about last week why we're doing so is because language models turned out to be, or the language modeling itself turned out to be pretty much a universal way to solve any problem. Just because the language, the human language is how we actually encode any kind of meaning that we can imagine. We use language to convey all those complicated, sometimes extremely concrete, sometimes extremely abstract notions among us. What that means is that almost any problem that we are interested in can be written down in language. And then almost every problem that we want to solve can then be written down as trying to fill in missing bits given the observed. And that's actually how we came all the way to the mask language model, because we wanted to make it a bit more general than left-right construction. Because although we talked how the auto-regressive language model can be used to fill in any of the missing bits, except that the complexity that is involved in trying out scoring all possible combinations in if you have an intermediate missing bits turned out to be too high. Unlike the mask language model where we just do the one-shot, let's say, prediction. But that aside, is that really the reason? Because it is pretty unlikely that the language model alone is going to solve all these different problems. OpenAI says that that's possible, but I'm pretty sure that's not true for many, many years to come by. Just for the reason of the complexity in the problems that we want to solve only grows. But that said, does that mean that this is pretty much of a useless thing? No, that's not true. It turned out that these generative models So we call them generative models, not because it generates anything, but because we model the distribution. So that's the generative model. And then the reason why we do all this generative modeling or learn about generative modeling is it turned out that the generative modeling is a way for us to use as many examples as possible to solve a very specific so-called discriminative problems like the classification. So let's get to that one. So it's going to be today is going to be very machine learning heavy. Although it's been kind of purely machine learning, so mechanics is actually heavier than that, but all right. So let's think about the classification. This is going to be both machine learning heavy, but also it's going to be very intuition heavy because a lot of things cannot be really specified rigorously unless we look at the particular problem. But anyway, let's try. So one way to think of a classification is to solving a constraint optimization problem. So what does that mean? So let's imagine that we're fitting some arbitrary, let's say the unspecified classifier, but only thing that we know is that the classifier has a number of parameters that we need to estimate. Then you can imagine that solving this problem is same as solving the optimization problem where I'm going to specify what kind of parameter configuration is reasonable before looking at the data. So something like infinite values probably are not the values that you want in your model's parameters. So then I'm going to say that this R is going to be infinitely high if one of the values in theta is too high. So you can imagine that this R is defining the hypothesis space over which we search for the solution. So I want to find the solution in this large space where the R value is really, really low. So you can imagine that the R could very well be squared function, right? So it can be the squared norm of the theta, right? In which case I'm saying that, okay, I hate anything that deviates too far away from the origin. But this is just an example. With the constraints, so it's going to be subject to d of y and f of xn theta is smaller than epsilon for all n goes from 1 to 10. And then this d is a per example loss. And this epsilon is some small value, right? So it kind of makes sense, right? So I want to find a parameter setting that is near origin, for instance, or within the region that I want to exist. But then I don't want a solution that's going to have too high a loss value for each and every training example and training examples I have. So this is just looking at it from the opposite direction from what we have looked at in the very first week of the course, is that there we said we want to minimize this per example loss. So it's going to be really, really small. And then that's how we found this theta. But here we're looking at the other side of the same coin, that is that if we want to find theta that is going to satisfy these constraints where each of the constraints corresponds to each training example, and then we want the per example loss to be small. So classification, or in fact any kind of machine learning problem where we can define a per example loss, can be written down as solving a constraint optimization problem. And then looking at this, what do you see here? What you actually see here is that if we have too few constraints, then the possible theta values that are going to satisfy this condition grows. And more constraints we have, which corresponds to having more training examples, we can narrow down our search space over which this theta makes sense. And what that means is that the chance that we are going to really find the true theta value for which this constraint is satisfied for all possible training instances goes up as we have the actual more training examples. Because the space of the feasible solutions theta shrinks as we get more and more training examples. So what that means is that we almost never have enough constraints, because the number of the training training points we can find is always finite. It's always finite. That's just because the age of the universe is finite. You can't really have anything that is infinite. It just doesn't work like that, right? So then what do we want? If we have only a small number of training instances that translate to the number of constraints, and then that was not enough, we probably need to just add in more constraints. Can we in fact then come up with another set of constraints using another per example loss, this time that relies only on the input? So on top of the set of constraints that come out of the labeled examples, so we have labels. What we want is that if there aren't enough, let's say, constraints, perhaps we need to constrain this optimization procedure by adding in a few more constraints, or actually a lot more constraints that rely only on the input. So we don't really need the labels, because often the reason why we have a small number of examples for classification is because getting the labels is very expensive. But on the other hand, if you have tons of examples for which we don't have labels, can we actually use them in order to further constrain this optimization procedure, or to constrain the space over which we find the correct data, the solution? And then what that means is that if we have a large enough n, and then assuming that satisfying these constraints are not going to rule out the true solution, that is, that these constraints do not remove a solution that actually satisfies these constraints, right? So yeah, there is a chance that after adding all these constraints, you can't really find the solution that satisfies both of these constraint sets. But assuming that that is not the case, it has an effect of reducing the variance of our estimator, because the subspace of the feasible theta just shrinks. Now then, the question here is what this d prime f prime should be. What should these two be? So let's turn this around a bit. So this is how we can view this kind of, let's say, classification of machine learning in the constraint optimization. And then by adding this unsupervised bit, this is often referred to as semi-supervised learning. Now, starting from here, let's come back to what we were doing originally. So what we often do is to look at the so-called Lagrangian dual. So whenever you have some kind of constraint optimization problem, you can turn this into an unconstrained optimization problem by introducing additional dimensions that controls whether you are violating the constraints or not. That aside, because that one you should learn from Carlos or John or whoever else who actually are actual experts in that topic. So in my case, I'm going to say that in practice, what we'll do is that we're going to try to minimize a dual loss function. That is the average of these per example loss functions, as we have learned, plus some the regularization term, or this R of theta, that tells us about the quality of each and every solution without looking at the data. It is multiplied by some, let's say, constant lambda that's often greater than 0. It's often greater than equal to 0. And then of course, if you want to be really strict, we can actually solve for this lambda as well. But in our case, that's actually totally unnecessary. And then the reason why we can't solve it is that there are a number of reasons, but I'll get to. Hopefully, I have some time to get to that later in the course, or you can ask Carlos. And he'll be able to actually tell you how he'll be able to give you the entire course, on this topic. And then you have to resolve this. We solve this problem with the stochastic gradient descent, and then we choose this lambda value by the validation model selection procedure. So that's what we do, right? Now, with this in our mind, and then with the assumption that we're going to use SGD, so we're going to use SGD, we want to talk about one quick thing about a property of SGD.
Missing one, right?
Sorry, what?
Repeat Brian.
Sorry?
We also have repeat Brian on over.
No, I'm just talking about the classification. Classification.
Oh.
This is the problem that we solved here originally, right? And then we're going to use the SGD. And then we're going to talk about one particular property of SGD before we continue this discussion. The observation is that the SGD cannot move too far. So it turned out SGD cannot move too far from where it starts. So what does that mean? Let's let's make a first observation. First observation is that the stochastic gradient is an unbiased estimate of the gradient. So that's actually pretty nice. The stochastic gradient is an unbiased estimate of the actual true gradient. And then what that means is that if I look at the actual, so this is going to be true gradient now. Then if I look at the expected value that I get, so I'm going to use the mini batch stochastic gradient descent. So I'm going to look at the distribution over the whole mini batches. Then look at the stochastic gradient, which is computed as the average of the per example gradient within the mini batch. Then if I look at what happens to the difference between these two is 0. So that's what it means. And then what that means is that as SGD approaches a minimum, on expectation, the gradient also shrinks to 0 because the true gradient shrinks to 0 near the minimum, right? So that's kind of the same thing that we're looking for. However, a bit of an interesting second observation is that the variance does not necessarily decrease to 0. So what that means is that if I look at the covariance over the mini batches of this mini batch based gradient, which was defined here, right? So let's just use this. Then what happens is that this one is actually greater than 0 almost always. So this is an interesting observation. If we did the actual gradient descent, not the stochastic gradient descent, and then assume that we somehow set the learning rate perfectly by asking some oracle to get us a perfect learning rate, and then as we go toward one of the nearby minimum, the gradient actually shrinks towards 0, and then at the minimum, we will actually have a very small gradient, so we're not going to make too much of the minimum. And on expectation, the stochastic gradient is indeed same as the actual gradient. However, the noise in the stochastic gradient, the noise comes from the fact that we are using only a small subset of the entire data set. That noise doesn't necessarily go to 0. There's no reason why that should go to 0. It only has to be that on expectation, it has to be a correct estimate of the gradient. But if you look at one mini batch at a time, it's going to change, and then it's not going to be 0 near the minimum. So what this says is that according to the first observation, SGD is indeed pointing toward the steepest descent direction on expectation at any point. And in particular, in the very early phase of training, almost any mini batch you choose are going to point toward the same direction. That's the point where the signal to noise ratio is extremely low or extremely high. It's very clean. We know where we need to move because this current parameter set, with the current parameter set, this classifier will fail at classifying any training sample, regardless of however you choose a mini batch. But then, as you get closer and closer toward the minimum, the observation too. So the observation that we make in the second case kicks in. So we're near the minimum, but then we cannot really hit the minimum because of the noise, And what is really interesting is that the SGD is going to escape the minimum if the minimum is very, very narrow. You can imagine that we're going to fit some kind of quadratic function to the minimum that we have, local minimum we have. And then if that one is really narrow, that can be somehow characterized as a trace of Hessian or whatnot, then SGD won't be able to stay there. As long as the noise is large enough, it's going to just jump out of the minimum, and then it's going to find the next minimum. So what happens is that we start from the beginning, and then SGD, because the signal to noise ratio is really high, it's going to, let's say, go to nearest, let's say, minimum. Then it goes there, and then as we near and near the minimum, what happens is that the noise now takes over. Signal to noise ratio drops, and then if the noise level of the noise is greater, then some kind of, let's say, scalar that defines the actual, let's say, the shape or the width of this minimum, then it's going to just jump out. And then as soon as it jumps out, what it does is that again, on expectation, we're going to look for the next minimum. Then it just does it until it finds a minimum that is wide enough so that it doesn't just jump out. And then what this actually tells us is that the SGD does not really explore the whole space of parameters. And then the solution it finds is very much a function of where SGD starts. And of course, this is a simplifying, let's say, picture of what happens when you train this kind of large-scale neural net with the stochastic gradient descent, and then there are so many interesting things that are happening. If you're interested in it, go to my homepage. There's a talk section. There is some speculative, let's say, talk on the stochastic gradient descent and deep learning. It's only slides, but take a look at it. It's quite amusing what happens with this stochastic gradient descent in large-scale neural network. Anyway, but regardless, the important thing is that what kind of solution stochastic gradient descent finds is strongly tied to where stochastic gradient descent starts. Because what it does is to find the nearest minimum, go in, and then if the minimum is too narrow, it jumps out, find the next nearest minimum, and then the SGD continues until it finds a nearest wide enough minimum, and then gets stuck there. So then, instead of trying to incorporate all these constraints that we can introduce using unlabeled examples, so the ones here, instead of ones here, can we use the idea that instead of introducing these constraints explicitly, can we use these unlabeled examples to choose a particular starting point of the stochastic gradient descent so that the solution that is going to form with the labeled examples are going to be better. So what do we do with the stochastic gradient descent often? We're going to randomly initialize the parameters. And then that initialization is where SGD starts. And then we're going to let SGD find the nearest solution. And then what that means is that even though we think that it's a super high dimensional space and everything, the actual space over which, or the subset of the space over which this SGD explores is pretty small. And then that's heavily defined by our random initialization. If you could initialize it in a different way, then that actually works as constraining the solutions, constraining the whole, let's say, space over which SGD finds, because it won't be able to come all the way back and find the solution. So what people have realized, a really long time ago, by the way, is that a very effective way to incorporate unlabeled examples is to use them to initialize the parameters for SGD. So that is, we can incorporate, that's not in English, right? We can incorporate unlabeled examples for initialization. What that means is that we're going to now split the training into two stages. Stage one, which we often refer to as pre-training, is where we're going to find a good region, good region in this primary space using all those unlabeled examples. So in this case, what we're going to find is that we're going to find a theta 0. That's going to be the arc mean. Of course, this is not exactly arc mean. Let's put it approximate. Arc mean over the space of the parameters using n many unlabeled examples. Once the stage one is done, then we're going to go into so-called fine-tuning stage. Then here, the goal is to find a nearby y minimum, where the nearby is defined based on theta naught. So here we're going to use the SGD. So it's not like necessary to use stochastic gradient descent there, right? But it is important to use a stochastic gradient descent on fine-tuning in the fine-tuning stage, because using stochastic gradient implicitly tells us that the solution that we're going to find will be near where we started. That is a theta naught. Minus this eta is going to the step size or the learning rate, 1 over the size of the mini batch. We look at each mini batch at update, and we look at gradient of d, y, of x, theta with respect to theta. And then we start this from theta 0. So it turned out this pre-training and fine-tuning procedure, which has been repeatedly discovered over time, turned out to be a very nice framework to incorporate all these unlabeled examples. Then what is the biggest question here is what should be this d prime and f prime? What should be the d prime and f prime? That is the question. And we are going to continue the discussion in 4 minutes. So let's resume at 6 p.m. Now it's 5:56. No, that's the question. What should we go for? So the best side of this
Essentially, yeah. Yeah, I don't think it would have earlier. At like 6:30 or 5:30. Yeah. Yeah.
Figure out.
Okay, all right, so we're getting better at going into a client mode, right? So the duration is getting shorter and shorter. So we'll see if we can actually get to the point at which you can actually predict that I'm going to the class, and then you can move to the mode. So that making the duration. So we can now talk about what D prime and F prime should be. And to do so, one thing we want to first talk about is it turned out that this generative modeling, that is to learn the distribution over what we observe in general, and the discriminative modeling are kind of the same thing. It turned out that that's actually one of the big realizations. Assuming that most of you have taken the, let's say, introduction to data science course or some kind of introduction to machine learning course. That actually doesn't help because I don't actually teach this in my own intro to machine learning. I want to talk about something that is relatively straightforward. So let's think about what the logistic regression classifier is. Logistic regression classifier that we looked at, so any kind of classifier that we have looked at was there in order for us to estimate this conditional distribution. So given the x input, what is the distribution over the prediction or the output or the classes, values, whatnot, right? So the whole goal was to try to get that one. The interesting thing is using a base rule, we can rewrite this as the P of x given y, then times P of y over P of x. Then you have what you notice is the P of x is the distribution over the x, the input, and then you have if our goal is to learn a classifier that is concerned with the relationship between x and y, the distribution over x probably doesn't matter. So we're going to simply look at these two terms. And then in the case of the naive base, we make this conditional independence assumption that makes it into P of y. And then we want to be P of xi given y. And then this is called naive base classifier. So this is called naive base classifier because if we do this, this is going to be base classifier. Now why is it base classifier? Because we use the base rule here. But then we are naive because we assume the conditional independence over all the dimensions of the observation x given the label. But we're not really interested in this. I just wanted to say this is naive base classifier, and then you must have already seen it from some machine learning lecture somewhere. But what we are more interested in this particular case is this base classifier. But this base classifier, or more often referred to as a generative classifier. So if you use a classifier to model this P of y given x directly, we often call it a discriminative classifier. If we train a model to approximate these two distributions and then use their product in order to do the classification, we call them generative classifier. So you see what I meant by these two turned out to be the same thing is that the generative modeling, that is that what is the distribution over our input observation, turned out to be essentially just the other side of the base rule of trying to predict, trying to do the classification. So this is often called a generative classifier. And then what does it mean? Is exactly what I said, is that the generative modeling and discriminative modeling are pretty much the same thing. So why is that so? Why is that so? Is because what is the best way to do the generative modeling? Let's imagine that we are going to, let's say, do a classification in the two-dimensional space. We're going to do a classification of the two-dimensional space. And then it turned out that there are two classes, so it's a binary classification. Then let's assume that they can be actually solved. It can be solved. Then what do? Is that I'm going to actually fit a one Gaussian on the negative class side and another Gaussian on the positive side. And then what is the distribution over the input then? The perfect one is going to be simply the mixture of two Gaussians. And then that's exactly what it says. So for each class, what is the distribution over the observations that belong, inputs that belong to that class? And then we just mix them with the probability assigned to each of the class, then that's suddenly my distribution over the actual observation. And if you recall from the very first lecture, so you probably can't recall it anymore, but we did learn about the mixture of Gaussian. And then what mixture of Gaussian did was effectively to say that for each and every Gaussian I see in this data belongs to one of k many classes. So the mixture of Gaussian is effectively the other side of a multi-class classifier. So what it tells us is that we can, if we know how to do the generative modeling really well, so that is that the unsupervised learning really well, that definitely has to help us in discriminative modeling as well. So what would be some examples? So I'm going to make up some examples. Let's go into the exactly same example we had about that. Let's say we're going to do the three-class classification. Then let's say in fact, the problems were so well defined that it turned out these were the actual examples we get. And then for each cluster, in fact, corresponded to different, let's say, classes. These are just the data points. So what you can see is that we are going to have a mixture of three Gaussians. And then this axis all corresponds to the samples generated from the Gaussian. And then let's say each of the mixture corresponds to the plus class, minus class, and zero class. And then all we need, if we could have done this unlabeled modeling, the modeling of the underlying data really well, then all we need is actually three data points, labeled data points. Each one telling us which of this mixture component belongs to, maps to which class. And then this is where the relationship between the generative modeling, discriminative modeling show up together. Is that if we know the underlying structure of the data really, really well, that means that one of those underlying regularities of the unlabeled data that is large enough has to correspond to the class structure as well. Now, let's think of the example that we talked about last week again on why the language modeling is so powerful. is because we said that the language modeling, in fact, indeed include all those interesting problems that we want to solve by the virtue of being trained to fill in some of the missing bits. And then that learning to fill in missing observations could be done without any labels. So question answering seems to be a problem where we want to have a lot of labeled examples, where the labeled examples corresponds to question answer pairs. But then with the language model, somehow we were trying to get the distribution over this language, and then that one actually included question answering within it. And what that means is that if we can model the data really, really well without any kind of labels, that modeling requires our model to uncover all possible ways in which we can model this data, and then one of them would correspond to the actual labeling of the data points. This really doesn't help, does it? Does it help? No. I guess no. All right. So that's the reason why I tend to go into the equations. Right? So in the case of the equations, even if we can't understand, it's just true. So we can just believe that it's true. Right? We're going to go into the. We're going to have a demo of what this means by going into so-called classification restricted Boltzmann machines. So I'm really a big fan of restricted Boltzmann machines because that was my PhD dissertation topic. We're going to go through it all together, and it was a very, very painful growing years working on RBMs. And then I'd love to have you all join me on this through some of the same things. So here, what we're going to do is we're going to build a generative classifier that has the X and Y. Then what did the generative classifier do? So here, if you think about it, this is same as P of X and Y. So we're going to essentially model the joint distribution over both X and Y. So that's what we're going to do. And then you're saying RBM may not be the fancy. So if you want to call it an energy-based model, that's perfect. This is one of the only examples where it actually works. So let's define the negative energy of X and Y. So this is essentially a score function that we've been talking about. So which pair of X and Y is good? And then how good is that? That's going to score. We're going to have, I'm just thinking. So we're going to have bias vector transpose X plus bias transpose Y plus sum over K equals 1 to capital K rho 1 plus X WK transpose X plus UK transpose Y plus CK. So this is going to be energy function. Now let's just look at it for quickly. So what does this Bx, this is a vector, right? That has the same dimensionality as the X, the input. So what this tells us is that regardless of what the Y is this X a good one? Right? So that's the kind of, let's say, bias that is specific to the input. Now, what is this By? Then that's the same thing. Without looking at the input, if I just look at this Y, which can be multidimensional, is if Y is close to well aligned with the B of Y, we call it as good. Right? So you can think of this as a prior over X, Y. And now here, what we do is that let's look at each individual, let's say, term within the summation. So if you look at the case one, what we look at is that is this XY pair well aligned with, given this, both the WK and UK, right? So this is where we try to look at how they are compatible, X and Y. And then we look at K different ways in which their compatibility is checked. Because you can imagine that there are many different ways in which X and Y are compatible. And the interesting thing is that this is actually almost exactly what we did already when we defined those classifiers at the very first week of the course. Except now we are looking, in fact, at this X itself. So we need to look at how good the X is instead of how good the y is given the x. That's the only difference. And then with this one, once we have a score, what can we do? We know how to compute p of x and y. That's using the softmax function. Then it's going to be, we're going to, so we're going to go look at all possible classes. So we're going to say that y is an element of a finite set, just because we're talking about the classification, although it doesn't have to. And then x is going to be some, let's say, real value things. X of and then given this energy function, we can also look at this conditional distribution over y given x. Because if you want to use it for classification, this is what we will do. Then here as well, we use the same kind of softmax function, but how we normalize is going to differ. We only need to normalize over y. Because now x is just fixed. X doesn't change.
Why?
C is a set of classes.
Okay.
So once we have this, then we can now train this model just like what we did. How do we train a model? We try to maximize the log probability assigned to our observation or the training data points. Now in this particular case, we notice that there are two types of the data that can be observed, and then three types of loss functions that we can define. What are two types? Two types are when we only look at input. Then two is when we look at both input and output. So this is going to be the unlabeled data, and this is going to be labeled data. Then we have a bunch of them. So we often have more of the unlabeled data than labeled data. But and then I said that there are three things we can compute. One is that I forgot to actually write something. Oops. Let's just bring it down a bit. Then now once we have these two things, in fact we have the joint distribution, we can also write P of X alone by marginalizing out Y. Now how do we do that? Is to simply consider all possible Y values and then sum the probabilities of all possible pairs. And then once we have this, what that means is that we have two different types of data, but then we can now look at three different types of loss functions. So loss functions can be derived from here, three, and then data, there are two types. The first one is the log joint probability of X and Y computed using labeled example. Second one is the log probability of the Y, the target, given the X using the labeled example. Then the third one is the log P of X computed using the unlabeled examples. So we can get all those functions. And then let me see. So you can imagine writing, and then we're going to look at just two cases here. You can think that when the unobserved, so the unlabeled example is used, then what we want to compute is the gradient of the log of the marginal, right? So there is this one. So marginal here, and then this turned out to be expected gradient of the log P of X and Y. Then what was X and Y? X and Y was just a joint distribution. And the question is then, what is this Q distribution? Q turned out to be X of minus E of XY over the sum over Y prime, X of minus E of XY prime, which looks very familiar because that is the P of Y given X. Let's just color that as well. This is this. So what this says is that the gradient of the log probability of one input that does not come together with the label is same as computing the gradient of the log joint probability of X and Y but we're going to try all possible values y can take. And then we're going to take the average, but when we do the averaging, weight is going to be given high, so higher weight is going to be given to the y that's more likely under our model. So what it says is that if our model says that this must belong to, let's say, class, a negative class, then we're going to say that, oh, yeah, we're going to use the gradient that we compute. So the log joint probability of x under that negative class, a higher rate. It just falls out from writing the gradient, but it's always a useful exercise. So what if we have a labeled example? Then we can just use the gradient of the log p theta of xy, the joint distribution directly. Then this one turned out to be minus the gradient of the energy function that we talked about of xy plus the expectation x prime y prime from p theta xy, the joint distribution. So expected gradient of this energy under the current distribution. So this is often called the negative phase, although it's positive there, negative phase where we look at what the model believes in, and then we try to make sure that the model does not believe in what it believes in anymore, while we're telling the model that this given xy is what it needs to believe in more. So you can imagine that this is what you see during the day, and then your brain is saying that, oh, what I see like this is highly likely. And then this is what happens when you sleep. You dream about it, and then often dreams are wrong. So we try to actually make sure that the dreams are going to have a lower probability. So then, this is how you learn this whole thing. Meanwhile, let me just color this. So this is going to be a joint, and that's it. So what does this mean? Is that we are using both the unlabeled and labeled data, and then as we use more and more unlabeled data, we actually can get a better estimate of p of x, and then p of x does have both p of x given y and p of y, and then from there we can actually extract p of y given x as well. So this classification restrictive Wolfram machine. Because what you see is that at the end of the day, this gradient of the log probability of x and y pure data shows up in computing the gradient of the log p of x. So what that means is that by updating or the estimating p of x better, how we estimate the p of x better using the unlabeled data is via estimating both p of x given y and p of y, which is proportional to p of y given x. So this classification RBM is a very nice example of demonstrating how the classification and generative modeling go hand in hand. And then they share a large portion of the parameters. So what do I mean by large portion of parameters? Let's just do a bit more algebra here, going back and forth. So let's start by looking at this energy function once more. It turned out that we can actually rewrite this whole thing by introducing one more variable called age. It's getting a bit repetitive, but well, once in a while, gotta do this kind of this exercise. So let's say we're going to define an energy function over now 3 variables: x, y, and age. And then age, we're going to call it as an expert indicator, or just a hidden variable. So that's the variable that we never observe ourselves. And we can rewrite this as dx transpose x plus y transpose y plus sum. So we're going to go for the k-many of them, hk. So this hk can be only binary. So hk is either 0 or 1. So that's why what I meant by the indicator of the expert. So we said that there are k different terms that tells us how compatible x and y are. And then we're just rewriting by saying that out of this k of them, only few of them are going to be active. WK transpose x plus UK transpose y plus CK. All right, so we can write the energy function over 3 variables instead of 2 now. Given this energy function, if you just do the derivation yourself, I did it, don't worry, I've done it tons of times, perhaps way too many times, but then you arrive at this expression. So probability of one of the experts activated given X and Y. So we're trying to figure out whether trying to say that the X and Y are likely, very probable under this energy function of the joint distribution, whether this Kth expert contributed to it. Right? So when we said that the X, Y are very likely, did the Kth expert contributed that or not? So that this probability is going to be sigmoid. So this is a sigmoid function of WK transpose X plus UK transpose Y plus CK. Yeah, okay. So this is just essentially a binary classification, right? So given the input, now we look at the probability of Kth expert being on. And then if you do the further derivation, the probability, this conditional probability, yeah. So the probability that Y is C, given H, now it's not X, but given H, is proportional to the exit of UC times H plus BY. So we're trying to look at whether, so we're just, actually, let me see. What about that? You transpose H. So you have to, oops, so this is actually, I have to be more careful. H, so let's call this a U bar. It's going to be where I'm going to just stack all these UKs. So U1, U2, and then UK, I have K of them. And then I'm going to take the seed column for this. So I'm going to just stack them as the row vectors. And then I'm going to take the column that corresponds to C. And then that I'm going to call it as a U bar C transpose H. And then similarly, if you do the derivation further, the chance that the X, the ith dimension of the X is on, so let's say everything is binary, although it doesn't have to, is going to be also sigmoid of Wi. So X is going to be binary in this case, H plus BX. R as well, R transpose. So all the same thing here. So we're going to stack them up, and then we're going to take the column vector of them. But the point here, the most important point is that in this particular case, let's say someone gave me X and Y. And then how do I know if that HK was 1? Is to look at the linear combination of this X and Y. Now I figured that out. But once I know what the H was, I can immediately tell what Y should be. Which Y is most likely. And I can also immediately tell what the value, most likely value of X is. Now, what it tells us is that this H, the hidden vector is the summary of X and Y. And then the summary of X and Y is about, and then that's the summary that was generated by the linear combination of X and Y. Now then, what that means is that and then once we have the summary, the predicting which class it would belong to is very trivial. So in other words, most of the parameters in this classification algorithm are going to be on summarizing. So these WKs and UKs, and then only a small number of the parameters from this UK is a small number of parameters that UK the WK is a majority because X is high dimensional. UK, where the Y is much lower dimensional because there are only a few classes, is has a very small number of parameters associated with it. And then what this tells us is that then perhaps the right way to do is to train a generative model on a large amount of unlabeled data, and then use those parameters as the starting point of the discriminative training. Because as the classification RBM tells us, the majority of the parameters are in figuring out the hidden variable given the input. That's where the majority of the parameters are. Very small number of parameters are there to figure out the class out of the hidden variable, the summary of the input. So what, in other words, what we want really is to use the generative model or density modeling as a pre-training stage. And then how that pre-training stage is going to go over is that this will be the density modeling or the generative modeling. And then large portion of this theta will be transferred to the parameters in the classifier. So the goal here is to do the generative modeling, use all the parameters, and add perhaps an extra couple of parameters to build a classifier. So it turned out that what we want to do is modeling the distribution over the input, and then that's what we have learned all along this semester. And then what is that in the natural language processing? That is language modeling. So we've learned already 2 different types of a way to do so. Now, is there any questions before we kind of say quickly go into the final topic of the day that we and using 15 minutes we have? Super clear or is it super unclear? So the important thing, what is the right way to use these unlabeled examples is to model the distribution of these unlabeled examples. Then once the modeling is done, we're going to use that distribution model as a backbone of building the classifier out. We'll look at one particular example now. Let me see. Okay. And then the example that we're going to look at is called continuous backup word, or sometimes people call it word to vector. It feels a bit old school. Yes, I understand that's from some time ago. But the interesting thing is that this is where the power of this kind of pre-training and fine-tuning or the transfer learning from the generative model to the discriminative modeling shows up most apparently. So we're going to look at the wording ranges. Then in particular, we're going to look at so-called continuous backup wording learning. And then we all know now already what continuous backup words is, right? What is continuous backup word? Is that we're going to model each word as a word embedding, word vector, and then we're going to consider it as a bag rather than a sequence. And then that allows us to simply sum them and then get a good representation of that backup word. And it turned out that continuous backup words is a way for us to build a masked n-gram language model as well. So what was the masked language model we had? Was trying to estimate the conditional probability over the missing words and TM given the corrupted version of the input. Oops. Where the corruption was to replace some of those selected missing words to mask tokens or whatnot, right? So we corrupt the input and then we try to recover some of the missing or corrupted portion of the input. And then one assumption we made was that these missing variables that are need to be reconstructed are mutually independent condition on this corrupted input. So what that means is that it's going to be product of I going from 1 to Tm, P of X, Mi given corrupt T and X. And then we said that this is the reason why we don't tend to sample, mask out and sample multiple tokens at a time. We always do it one at a time. Because this is a huge assumption we already made. And then we're going to make another assumption that is akin to Markov assumption. What we assume is that for each and every these conditionals, so MI, we're going to only look at nearby words. So we're going to look at MI minus N over 2 to X MI minus 1. And then we have the mask here, right? Mask, and then X MI plus 1 all the way to X MI plus N over 2. So what happened here? So before we were looking at the entire sequence, but now we are only looking at the n many words that are surrounding the center word that is missing that we need to predict. So it's something akin to the Markov assumption, right? So instead of looking at the entire thing, we're going to say that whatever is nearby are most relevant. So we're only going to look at them and then ignore all the others. Now what that means is that we just need to now figure out what is the right way to parameterize this. What continuous backup word, what Tomasz Mikolov did in 2011, 12, something like that, was that let's use the simplest possible linear classifier. Because there is still a classification. And in fact, this is a very simple text classification problem because we have a fixed number of words input, and then there's a one word that needs to be predicted, and then the vocabulary is the class. So let's write it down. So what do? We always write down the score function. And then here, what we have is xmi minus n over 2 all the way to the xmi in the middle, all the way to the xmi plus 2 over n. So this is the entire thing we get. The input is on the left and right side of the center one, and the center one is given because we are scoring them. And then what Tomasz did was to let's embed each of these words and then simply look at the dot product. So here as well, so let's see. J going from m minus 2 to m minus 1, embedding of the xj plus j going from m plus 1 to m plus n over 2, embedding of xj. So this part is this is where the continuous backup word comes in. So we get the continuous backup representation of the input, that is the surrounding words, and then we compare it against the output, that is the xn, the center one, and then we do that comparison using a dot product. So this is just like a linear classifier we learned, and then we have used all along since the beginning of the course. And then given this core function, how do we recover this probability? With the soft links. So we're going to go through all possible words that can show up in the middle. And then we score them, we exponentiate all those scores and divide all those scores by the sum of them so that it's going to sum to 1. Then that's how we are going to build a continuous backup word, in some sense, let's say Markovian masked n-gram language. So that's how we're going to build it. And then we know how to train it, right? But then the one thing you notice here, in particular, if you recall from our earlier lecture, this is really the definition of the distributional semantics, right? Or the distributional hypothesis. If you recall what distributional semantics or the hypothesis was, is that the meaning of the word is determined by the other words that appear together. And then what this says is that how good this choice of the word in the center is entirely dependent upon all the other words that are coming together within some, let's say, n-gram window. And then how do we train this? If you recall from the Gaussian derivation that we give with hands for the training a text classifier, we are going to make this embedding of the correct center missing word to be as similar as possible to this continuous backup word representation of all the surrounding words. While incorrect choice of this missing word is going to be pushed away from the continuous backward representation of the surrounding word. That is truly what distributional hypothesis actually tells us the semantics should be. So this continuous backward was really popular because of this properties that it really does tell us a lot about. It really is a one, but very, very explicit way to encode this distributional semantics. Now, let's say we train this model on a very large amount of data. And then we can train it extremely efficiently. So all we need to do is have one vector for one word in your vocabulary. And then everything is just dot product and summation. It can be implemented extremely efficiently. It was one of the wonders of the Tomasz Mikolov, who was defeating this kind of model on a Wikipedia with the entire internet on his laptop. And then his laptop wasn't even there because he was able to optimize it really well. And then this model is really straightforward in terms of computation. So now we have trained this model, and then what do we end up with? Because this model doesn't really have too many parameters. Only parameters are these word embedding vectors, this table lookup later, this table. We got the table. And then what really worked well is that all you need to do is you just use this table as a drop-in replacement of the word embedding layer that you're going to use. So why should that actually help? And then you're going to just put whatever the neural net on top of that, as long as this pre-trained continuous backward representation is used. Why would it help actually, if you think about it? So we decided to use this word embeddings we got from the continuous backward mask language model, and then we're using it. So why should it help? Let's imagine that we have a very small number of labeled examples. And then we're going to use these embeddings, but we're going to fix them. We're not going to update them. And then let's imagine that we are going to build some kind of sentiment analysis. So we're going to look at the movie review written by a viewer. And then we're going to see if the movie reviewer was happy or sad watching this movie. And then let's say in this very small training set that we have collected by talking to all those movie reviewers and critics, turned out to not have a single occurrence of word love. So no critic decided to use the word love in this small data set, which can always happen. It's very easy for that to happen. But it turned out that because these critics are, like highly sophisticated, they decided to use adore instead of, let's say, love. And then interesting thing is that in this kind of pre-training scheme, in this distributional hypothesis, it tells us that the adore and love will be close to each other because they do appear pretty much in the same context. So what that means is that those vectors are going to be really, really close. And then even when we train a classifier that uses this word embedding, only using the word love, adore or like as associated with the positive sentiment, when the word love shows up from this classifier's perspective, that's the same word as like or adore. And then you can actually tell that, okay, that must be signaling the positive sentiment of this review. So what that means is that by having this well estimated vectors, word embedding vectors, that comes out of this modeling the distribution, what happens is that in the fine-tuning stage, now classifier can actually generalize to the things that are unseen during its own fine-tuning because the label data was small. Essentially, we did not have to have the labels for all possible ways in which the word like could be used in this sentiment analysis. All we needed was just one occurrence because all those synonyms are going to have very, very similar words. So classifier can't tell the difference between like and love in that case. So that's how you generalize better by using all this large amount of labeled examples, and then fine-tuning the model on a very small number of labeled examples. In other words, the unlabeled example, like the text that has no labels, worked as a constraint to decide what the word embedding vector should be, even for the words that were not seen in the fine-tuning time. So the labeled example. And that's how we go all the way back and then make a connection to the very beginning of today's lecture. That is that the classification is the is equivalent to solving a constraint optimization problem. And then using all these unlabeled examples can be equivalent to introducing all those extra constraints so that the classifier is going to have a lower variance and thereby generalize better to the same example. And that's it for today. And I will see you all next week.
I also think